Okay, so in this falling film, as you can see, there is a reservoir here in the liquid in, and then there is an effect over here, but we will ignore the end effect. And then you see the disturbance are neglected, and then the W, or the width of the falling film is actually much larger compared to the film thickness, so we can write it W. Okay, and like that. Okay, in the previous one, in the shell balance or shell momentum balance, we have to make the thin shell, and then after that we make the shell momentum balance, and after that we try to rearrange the equation until we get the equation, yeah, for the differential equation for the momentum, flux momentum. And after that we do the integration with some boundary condition, and then apply the Newton's law, and then do the integration again with another boundary condition related to the velocity. Then we can get the velocity profile of the velocity. Okay, and now let's try to do this using the equation of change. Okay, so what you need to do is you have to open your appendix B, and then try to identify which equation you should put into our the problems. Okay, so as we know that sorry. Okay, so as we know, wait, let me right here. So we will have Cartesian coordinate. Okay, why this is happens? Let me try to do it again. Okay, so okay, so we need to have a Cartesian coordinate, yeah, with this one. There are so to get this equation, so you have to go to the appendix B and then find about the equation of continuity. So one of the skills is you have to identify which equation that is appropriate for this case. Okay, the first one is called the equation of continuity, and then identify the coordinates. Okay, the coordinates is Cartesian, so you have to pick the equation continuity for Cartesian coordinate. Okay, so this actually so this is the equation. Okay, I think now with if you're using tablets, you can just make a screenshot and then copy them into your Word or your tablet, your sheet, or if you're using paper, just rewrite the equation. Okay, so when you write the equation, that is 1 point. Okay, and after that identify all of the condition here. Okay, for example, if it is steady, so we know that it is steady, yeah, so we know that it is steady. So because it's steady, then this would be equal to 0. Okay, and then we don't have Vx. Okay, so we also know that Vx to phi to the x is equal to 0. So this also would be equal to 0. Okay, so and then phi to the y also 0, equal to 0. So that will live into this one. Okay, so so d over dz of rho phi z equal to 0. So that's why the phi z is actually constant. Yeah, so phi z is not function of z. Okay, so this equation of continuity is actually tells you why phi z is actually a constant at certain x. Okay, why phi z is not a function of the direction of z. Okay, so this is actually based on the equation continuity as well. Okay, what happens if phi z is changing? Phi z is actually changing if the area is changing. Okay, do you know, have you ever tried to pour what's called condensed milk, susu kental manis? Okay, if you open from a can, if you open the condensed milk, you know, with some opening can, like quite big, like 2 centimeters, and then you pour it like this into your to your glass, okay, as it is running down there, the cross section of the fluid is actually become smaller, okay, and then the velocity is become higher, okay. So but however it doesn't actually relate it with this case, okay. So that is the equation of continuity, yeah, okay. The second one is the equation of motion, okay. The first one, you have to there are two types of equation of motion. There are the B5 and also B6, okay. So it really depends what you want to looking at, okay. So first you have to identify the boundary condition first, okay. And identify boundary condition around your phenomena or around your system, and then identify which boundary condition are available, okay. So if we go back to here, we know that if this is the Cartesian coordinate, this is to the x, this is to the z. We know that at x equal to 0, do you remember what is the boundary condition when x equal to 0? You can open your notes if you want. What is the boundary condition when x equal to 0? Do you remember? Or okay, or if not, let's try to identify what is the boundary condition in this system. Okay, anyone would like to have a volunteer?
When x equals to 0, it's the liquid gas interface book.
Yes, and then?
So the shear stress is equal to 0.
Okay, or tau xv, yeah, equal to 0. Okay, yeah. What is another one? Do you have any other boundary condition in here?
When x equals to delta x,
Delta.
that's the solid liquid interface book.
Yes, and then what does it mean?
The fluid velocity is equal to the solid velocity. So since it's not moving, it's equal to 0. Yeah,
Yeah.
I'm not mistaken.
So that would be so the velocity of the Vz would be equal to 0, yeah? Right?
Yes, book.
Okay. So here we have two boundary condition. This is the first one. So this is the boundary condition 1. This is boundary condition 2. Okay, so you can so we have one boundary condition related to the momentum flux, okay, so or to the shear stress, and we have a boundary condition related to the velocity. Okay, so because we have a boundary condition related to the shear stress or to the flux momentum flux, here we can use the equation of motion in terms of tau. Okay, but if not, then if only the boundary condition only related to the velocity, you can write the equation of motion in for the B6, yeah, because we're in the right term here is all about velocity as well. Okay, so here, so what I do is actually, okay, so I find the boundary condition, and then the boundary condition we do have some related with the boundary condition with the momentum flux, and the second one I identify, okay, I need to use the B5, so I open my appendix B and then copy them with a screenshot, or if you're using your paper, write it, okay, and then because it is in the because actually in this one in the term of z, yeah, okay, because the motion is in the direction of z. If we go back here, yeah, the motion is in the direction of z, okay. So so the motion in the direction of z, and then the momentum is in the direction of x. Okay, so then we can see which one here that we looking at. Okay, so here that there are three in Cartesian coordinate. There are three direction or three equations that we're looking at with the direction of x, y, and z. Okay, because the velocity is caused at the phi z, then we can it depends to you. So because it is about x, so we don't need to write this one. Okay, and also to y also we don't need that one. Okay, so then we're gonna use this equation. Okay, so we're gonna use this equation because the velocity in the direction of v. Okay, and then again then what you need to do is try to identify one by one. Okay, so dou phi z over dou t. So is the this again tells you about if the system is steady or unsteady. Okay, the system is steady, so there is no changing of velocity to the time. Okay, so this would be equal to 0. Okay, and we know also that there is a vx is equal to 0, so we can make it this 0. Vy also equals to 0. Dou vz over dou z equal to 0 from the previous the equation of change. This would be equal to 0. Okay, dou p over dou z. Do we have this one? Dou p over dou z in our system, in the falling film system. Go back again. If you're not sure, go back to here. Do we have dou p over dou z? Remember the open system and a closed system? So what do you think? What is the value of this one?
0, Bu.
Yep, 0, yeah, because this is a open system. Go. Okay. If you're not sure, think again, go back to the phenomena and try to imagine the phenomena. And okay, so it is open system, so it would be equal to 0. Okay, and then dou tau x over dou tau z, and then I think this there is a value for this one. Tau yz over dou y, we don't have this one, and tau zz also we don't have this one. Okay, so in the end then we will, so from here we will have 0 equal to minus dou over dou x of tau xz plus rho gz, or dou over dou x tau xz equal to rho gz. Okay, so see, so actually you can get similar result in my, I think if we know really know which one is 0, which one is not, which one is non-vanishing velocity, non-vanishing components or not, we know the boundary condition, it looks easier for us, yeah, to do this one. Okay, and then after that what you need to do, just do the integration, for example using the tau xz equal to rho g z x plus c1, while you have to check what is gz, yeah, for that one. So gz is the g cos theta and so on, and then you just can continue. Okay, so that is one. So for one phenomena, you can use it using the shell momentum balance or equation of change. Okay, if in the exam you may choose between those two method, you can choose any which one you like. If you use this one is easier for you, just use the equation of change. Okay, but if it is really stated okay, you have to use the shell momentum balance, then you can make the shell momentum balance. But at least if you redo the calculation with this equation of change, you can make sure that your calculation is all right. Okay. Okay, so for this case, so let me stop it here first, and then do you have any questions or which steps that you would like me to explain again? Anyone? Is it quite clear? Okay, I think now I would like to ask maybe Ayu. Ayu, what do you think? Do you find the difficulty with this equation of change?
For me, it's fine, Bu.
Okay. Which one is better? The previous one, the shell momentum balance, or the equation of change? Okay.
I don't think it's much difference, Bu.
Okay. Yeah, but this one, the difficulty. So, but still, yeah, about the concept, the non-vanishing components, you need to know the boundary condition. You need to know the phenomena. You also need to know. Okay. So all the phenomena, how you describe, it is the really key points for you to do it. All right. So let's check again the second one, the cylindrical wait, the cylindrical tube. Yeah, this one. I think I have explained this one last week, but let's try one more just to get one by one again. Okay, so the second one is this one. Yeah, the flow inside cylindrical tube. Okay, again you have to remember about the what is the non-vanishing components, what is the boundary condition related to this one, okay, and also again the coordinate. Okay, so first one you have to know the coordinate, okay, and it should start when L equal to 0. Okay, so don't write it here, don't write it there, or don't write it just slightly down there, but at really when L equal to 0. Okay, because we need the coordinate as well for Z. Yeah, when Z equal to 0 there. Okay, so that is the coordinate. So once we know the coordinates, so we know that it is a cylindrical coordinate. So the next step, so you need to find the cylindrical coordinate for both equation of continuity as well as equation of motion. Okay, and then another one also, we need to identify the non-vanishing components. Okay, so we know that we have phi, which is the phi is a function of r with the radius, and then we know that there is no phi r. So phi r is actually phi that flow from here to that one. Okay, if it is for example, if we have a well or mata air, yeah, like that, and then the water flow from down and from above, just below the ground, and then try to spread it like 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 the radially, that it is a VR. Okay, like spread like that, make it bigger, that is VR. Okay, but for this case the VR is equal to 0. Phi theta is actually when it is butar ya, with angular velocity, that is phi theta. So now we don't have phi theta as well. And the third one, we have to identify again the boundary condition. Okay, we know that at the boundary condition in a pipe, at when r equal to 0, or in the actual axis, there would be a maximum velocity. Okay, or the tau would be 0. Then we know that an r equal to on the wall, that the velocity would be equal to 0. Okay, so the boundary condition, we know that at Vz, when r equal to 0 would be maximum. Okay, or tau rz at r equal to 0 would be equal to 0. And then the second boundary condition that we know that phi z at r equal to on the wall would be equal to 0. Okay, so sorry, but I think for this one, I don't know this one. Yeah, I think I'm not really sure this is the right correct, so I'll just write it like this one. Okay, now, so the next step is Neng Neng, Aisyah, close the door, close the door, close the door, tutupin. Okay, now, so the first one that we have to check is the equation of continuity. Okay, so again, you can prepare it beforehand. For example, before the exam, put some screenshot that you need, and then put it there. Or if you're using your paper, pencil and paper, pen and paper, you just rewrite the equation. Okay, it is a good thing for you as well to just write the equation. I like to write equation as well in my notes. And after that, so here we can identify the equation for continuity. Okay, so this is the rho over dou t because it's steady, so it's equal to 0. Okay, and here 1 over r dou over dou r phi rho phi r. There's a phi r over here. Okay, so phi r would be equal to. So what is the value of phi r?
0.
Okay, so this is 0. Okay, and then this also there is a phi theta, so we can also equal to 0. So it leaves into just dou over dou z of rho phi z equal to 0, so that means dou v z over dou z equal to 0. Okay, so see, so this is actually the evidence pembuktian that the phi over dou phi z over dou z at this time is equal to 0. Okay, and the second one is the equation of motion. Okay, so you have to be careful about this equation of motion. There are two types here. There are two types of equation of motion. The first one, that the one that has the tau in it, the appendix B5. Okay, the second one, the equation of motion that have only the velocity term here, the appendix B6. Okay, so which one should I use, the equation B5 or equation B6 from that one? Okay, especially when you write it using your pen and in a paper, sometimes you have write quite long, and then okay, I think it's wrong and have to change it. Okay, so we have to identify. Okay, how to identify? Again, check the boundary condition. Check the boundary condition. What is the boundary condition related to? Most of them. Okay, so here we have the boundary condition related to the velocity on r equal to 0 on the axial axis. The second one at a velocity r equal to r. So both of the boundary condition is actually related to the velocity. Okay, because it is related to the velocity, it's gonna be difficult if we use appendix B5 as our equation of motion, because here you have the tau RZ, tau. Okay, get it? Is it bigger enough? Okay, this one, yeah. So this has all the taus. Okay, so for this case, don't use this B5 for the tau z for this one. Use this one because we have boundary condition related to velocity. Okay, yeah, because we have boundary condition related to the velocity, then it is better if we use the B6 or equation of motion related with the velocity. Okay, so again, the equation that we're looking at is actually the one that actually in the direction of the flow. Okay, the flow is actually in the direction of the gz, or sorry, in the direction of z. Okay, so then we can use the gz over here. Okay, it is okay if you want to write this one, gr and g theta. Just want to check some, maybe some, some, for example, what is the difference of pressure with r, for example, like that. It's fine as well. Okay, but if we, because we were thinking about the momentum flux, then we need to write it with dgc. Okay, so write this one. Okay, make it a little bit bigger. Okay, there, so that we have Vz over dt. We don't have this one, okay, because it is steady. Okay, we don't have Vr. Okay, we don't have V theta, and then we don't have dou Vz over dou z from the equation of continuity before. Okay, so this actually equal to 0 from the left hand side. Okay, dou P over dou z. Do we have dou P over dou z in this case, in the cylindrical tube?
It's an open system as well, right?
Open system or closed system?
Does it have a wall in this case?
This one is inside the pipe, full fluids. So it's open or closed? It is full of fluid, so it is
Oh, it's closed. No?
it's closed system. Yeah, so it's closed system. So we have dou P over dou Z, and then mu. Okay, and then this one over r, dou over dou r phi z over dou r. There are phi z over dou r, yeah, because the phi z is function of r. This is a second derivative, so it would be equal to 0. Why second derivative becomes 0? Because if the first derivative is 0, phi z to the theta is 0, so the first derivative is 0. Of course, the second derivative also 0. Okay, this also similar with this one. The first derivative of dou phi z over dou z is equal to 0. Okay, of course, the second derivative would be equal to 0. Okay, so this is what I think I can give some explanation. So if phi z is actually a function of r, so that means dou phi z over dou theta, of course, equal to 0. That is first derivative. Okay, the second derivative, if we derive this one again, dou square phi z over dou t square, of course, equal to 0. Okay, so if the first derivative would become 0, the second derivative, of course, becomes 0 as well. This also similar with this one. We know that dou phi z over dou z equal to 0 from the equation of continuity, from this one. Yeah, this one from the equation of continuity. Okay, so if the first derivation is equal to 0, the second derivative, of course, would be equal to 0. That is how you mention between first derivative and the second derivative. Okay, if the first derivative is function of something, for example 2x, so when the second derivative would be, so you have to derive that 2x equal to 2, so you have the value. But if you have first derivative equal to 0, then the second derivative would be equal to 0 as well. Okay, so it will leave that would be this one would be equal to, we have the minus dou p over dou z. Okay, and we have that rho gz, and then plus this term. Okay, that plus maybe I'll write it here, mu 1 over r dou over dou r dou phi over dou r. Okay, so after that once you get this, so this is the equation, and after that you just need to rearrange them. If you remember in the shell balance, they combine them together, become those like P, yeah, like the P minus rho g h, yeah, something like that. That should be that's fine as well. Okay. Okay, so and after that it's all about the mathematics and then how you solve it, and then if you look at here, there are two derivative here, so you have to do you have to integrate this one. You have one boundary condition, and then you do the integration of this one. You have two a boundary condition, and then those boundary condition related to the velocity, and we have two boundary condition related to the velocity. Okay, so I think so that is an example how to use the equation of change for the examples in this one. Okay, so let me stop here again, and then anyone would like to have any questions? Okay, no, right. So okay, so I think I can stop it here, and then maybe I can open the birds book for the next one just to make sure. So if you need more explanation, you can open the birds book. Where is it? Okay, so for example, wait, so this one, so this is actually the example is in the this one, yeah. So for example, this is the use of equation of change solve problem. This one this is from equation of continuity, motion components, and so on, yeah. That would be here. And then this is the rework of the steady circular flow. So in the end you will end up with the equation of continuity over here, and also the equation of motion, yeah. This is quite similar with this one. Then we may introduce again the term of large P. Okay, where the large P is actually P plus rho GH, where H is the height above some arbitrary datum plane. Okay, and then after that we have to do the integration, the second one, and then the second integration, then we'll end up with some boundary condition there, yeah. So that one there, therefore for boundary condition, and then again the resulting solution is similar with the previous one with the mass balance. Okay, so now I would like to have another example. Okay, this one. So I will use the book first before the PPT. I think my PPT hasn't finished for this one. So now let's talk about the next phenomena that is actually used also using this equation of change. Okay, I think I have to close the door so it doesn't really noisy. Okay, so what I'm gonna do is what we're gonna looking at is actually the problem on a quad fiscometer. Okay, so quad fiscometer is actually a device which is used to measure the viscosity of a thick liquid, a very viscous liquid. For example, lubricants, plumas, or ketchup, yeah, or what else? Like I think usually more about all the viscous lubricant yang kental, yeah, like that. Okay, so this is the schematic. Sorry, this is the schematic of the equipment here. Okay, this is the schematic of the equipment. So you have there is a fix here, and then there is something, the cylindrical, that is moving, like rotating. So because it is rotating, that it will have angular velocity, it will have v theta. Okay, and then it has length of kappa r. Okay, this one, you can look at the blue one over here, yeah, this one, look at the blue one over here. Okay, and then we have another bigger cylinder for the container with the radius of r. Okay, so and what they do is actually we rotate this one. Okay, rotate the inner cylindrically while the sorry, is it the stationary, or sorry, we rotate the outer one. We rotate the outer one with the angular velocity of omega 0. Okay, so we rotate the other one, and just keep this one fixed. Okay, so and after that, because it is rotating, there would be some shear or angular shear stress, something like that. Okay, and then they would have some, and then they need the force, and then they measure the force. Okay, and after that they can calculate how much the viscosity for that one. Okay, so that is the quiet viscosity filter. Okay, but before that, I think I need to explain to you again that actually in have you ever seen a viscometer in lab tech to measure the viscosity of fluids or alcohol or water?
The one
that is like tiny long like that with the very thin cylinder. Have you
the
seen
one
that?
that looks like a YouTube, right, Bu?
Yes, like that. Okay, now that's the thing. So in viscometer, in viscometer, it actually use the cylindrical. I think before this, let me explain to you about the viscometer there. So in the viscometer, it's actually they use this flow circular tube. So this one, yeah. So this actually used to calculate the viscosity and the viscosity, because in the end, so I think there's some explanation about this one. Let me explain to you. So the application of that one is actually we can determine the viscosity from the capillary flow of the data. So if you look at the viscometer, it has a very long, quite long length, yeah, and then a very tiny diameter inside that, and then you try to flow them, yeah, flow the viscosity, and then you record the time, right? And then I don't know if you have done that one or not, but that's actually the principle of viscometer. And in this case, because so the viscometer is actually can for laminar flow, it can we can rework that one with this one, which is called Hagen-Poiseuille equation. If we know the pressure drop, we know the radius of the the capillary tube, and then we know the mass flow that is flowing, and also the length of the viscometer, we can determine the viscosity of the flow. So that is if the viscosity is laminar and the fluid is Newtonian. Okay. That is one of viscometer. Okay, but if in here the viscosity should be quite low, and then also it's quite should be like runny fluids, yeah, like water or alcohol or just I think aqueous solution and so on. Okay, but for very viscous problems or viscous fluids, we can it would be very hard to measure with this one, so we're gonna use with the this one, the wet viscometer. Okay, so here let me explain again. So the viscosity may also be in the torque. Yeah, so here we can measure pressure difference and mass flow through a cylindrical tube. This is the basis, the determination of viscosity in commercial capillary viscometer. Okay, so the one that you know is actually capillary viscometer. Hopefully in this lab tech 2, yeah, you can also touch the device and then do the measurement with that viscometer. Okay, but for the viscous fluid, we're gonna using the determine by measuring the torque. The torque is actually force multiplied with the radius, okay, required to turn solid object in contact with fluid. Okay, usually for the lubricants. Okay, so here the fluid is placed in a cup, and the cup is made to rotate with a constant angular velocity of omega 0. Okay, so O stands for outer. Okay, and the rotating viscous liquid causes the suspended bob to turn until torque produced by the momentum transfer in the fluid is equal to the product of torsion constant kT and the angular displacement of theta b of the bob. The angular displacement can be measured by observing the deflection of a light beam reflected from the mirror mounted on the bob, and the condition of measurement also controlled that there is a steady tangential laminar flow and annular region in the two coaxial cylinder. Okay, so this is actually the two coaxial cylinder. The coaxial cylinders means is in the similar axial, yeah, satu as, ya, satu axis. Okay, so we have the inner rotatory cylinder, which is 0, and we have the outer rotating with the v theta. Okay, so in this case, then so after this, I think it's almost 8:45. Okay, so here, so for the solution, if we look at here, then it's actually in here, because they're rotating like that. Okay, so there is do we have phi z? Do we have phi z? Phi to the direction of z?
No, you.
No, yeah.
I don't think
Okay,
so.
so this is phi z, yeah. So we don't have fluid coming, going that way, right? They just rotating. Okay, so we don't have phi z. Do we have phi r? Phi to the direction of that one. We don't have phi r as well, okay, because it doesn't, the fluid doesn't spread it out like that, but actually the fluid only rotating. Okay, so rotating, mutar. So that means because of rotating, because of the angular velocity of omega 0. So we have phi theta. So here we have phi theta, which would be a function of r. When r equal to k kappa theta, because this is all stationary, we don't have that one. Okay, and then while in the r equal to capital R, on the outer one, the fluid rotating with phi theta. Okay, so here we have the solution. Okay, so here we have the solution. The first one is phi theta would be equal to phi theta function of r. Okay, we don't have VR and we don't have V theta. And then the pressure we don't know, but looks like the pressure would be a function of R and Z. So the pressure would be function of radius because of the centrifugal force, and maybe the pressure also would be a function of Z because of the gravity. Okay, so we will continue again next Friday, but let's have a look. Try it by yourself. Can you get this term for the R component, theta component, and Z component using those equation? Yeah, and also you have to think which equation you need to apply. Is it the equation of motion with the theta or with the velocity? So be careful, check again. So looks like the boundary is only about the velocity that we know, so you can choose the equation of motion related to the velocity, and after that we will get this one. All right, okay, I think this is just the introduction, pengantar for the coed viscosity method, and then on Friday we'll I'm gonna explain more about this coed viscometer and also about the another one, yeah, the turbulence and so on, and then we'll see again about that one. Okay, now before we close the class, anyone would like to have any questions, or is it enough? Okay then, all right. Okay, so this is the introduction for the coed viscometer, but looks like the time is quite limited, so we're gonna continue again on Friday. Okay, thank you everyone, and have a good day.
Thank you very much, Bu.
Thank you,
Very much.
Bu.
Okay, thank you. Bye bye.